Okay, welcome back. Our next presenters are both Embedded Vision Summit veterans from the same company. On stage with me right now is Girish Venkataramani. I'm going to do this. Venkataramani. Close enough? Yeah? Okay. Product Development Manager from MathWorks. And coming up after him will be Avinash, who I know as Avi. Nehemiah, Product Marketing Manager for Computer Vision, also at MathWorks. Thank you.
Thank you. Good afternoon, everyone. So over the past couple of days, we've heard a lot about deep learning on various kinds of hardware platforms. We've had the hardware vendors give us good talks about new technology, which is available now to put your machine learning models on hardware. There's a lot of libraries and whatnot. However, when it comes to your algorithm, the algorithm designer, what is that workflow to get from your algorithm and put your software on the hardware? So we've heard about deep learning and all the frameworks and the inference engines targeting this hardware. But an application is more than just deep learning. Deep learning is usually a piece of your application. I'm going to talk a little bit about that and show you some examples of what I mean. So in this talk, we are describing a workflow from MATLAB to hardware. So MATLAB, as we all might know, is a premier language for algorithm design. And we've been using it, people have been using it for image processing, computer vision, machine learning for many years now. And we have we're going to show you what we've been doing in the deep learning domain. So there's a lot of hardware platforms available for deep learning today. So if you want just raw performance, you might go with a GPU. If you want energy efficiency, there's ARM, there's FPGAs. There's a whole mix of different choices when it comes to machine learning hardware. However, when it comes to software, there is this fundamental trade-off in programming languages. So I'm a compiler designer. For me, this is a thing which has defined innovations in compilers for a while. So on the one axis, on the x-axis, you have ease of programming. So how easy is it to express your algorithm? And then on the y-axis is performance, right? So if you want to get really good performance, usually you would have to deal with languages like HDL, CUDA, SIMD, and whatnot. And it's hard to program. It's not very easy. On the other hand, you can write your applications in MATLAB or Python, may not get the best performance. So what compilers do is give you a route from these high-level languages to hardware-specific languages. So I'm going to talk about our a bunch of code generation tools that we created to enable this path from MATLAB to different hardware platforms. So here's an example, right? I have a simple ax plus y vector math. And this is, of course, completely parallel. It's a loop, and every iteration is parallel. If you have a large vector, you can do this in parallel. Now, on the right is the code that you would have to write to do this on, let's say, a SIMD instruction set or on a GPU using CUDA. It's not very intuitive as the left. In fact, with MATLAB, you can do this in one line of code because MATLAB supports vectorized operations. So vectorized operations means operations which can process matrices and vectors. So I'm going to present coders or code generation tools which allow you to move from the left to the right. So write your algorithm in MATLAB and generate code for GPUs and SIMD architectures. So when it comes to deep learning, the problem is also similar. It's not just about your deep learning application. So TensorRT, the deep learning inference engines that Intel has talked about, ARM and N, these are all inference engines, right? They're really good for inference on the hardware platform you want to target. But application design involves more than just deep learning. So if you take a typical autonomous system, it involves perception, some localization and mapping, planning, path planning, controls. And typically, deep learning is used at the perception stage primarily. So what about the rest of the application stack? And even if you take a perception algorithm, so I'm going to talk about one, traffic sign recognition, or any kind of detection recognition algorithm. Here, we have defined an algorithm which uses two deep learning networks. So there's an object detection network, and then you do some processing on the outputs of that network, and then you run it through a classifier. So the object detection tells you where the traffic sign is, and the classifier network tells you what the traffic sign is. So you can see that just having inference engines will not be sufficient to solve problems of this nature. So what I'm going to talk about is a workflow in MATLAB where you start with designing your model, your deep learning model. So MATLAB is a framework which allows you to train your deep learning network, but it gives you more than that. It's not just training algorithms. Part of training is getting your data in place. So you can have a large training data set, and how do you manage that? How do you label that? We have some automated labeling tools, and Avi will talk a little bit about that in the, later in the talk. And then you can train, and we can scale the training to GPUs in clusters on the cloud and whatnot. You could also train your models in Caffe or TensorFlow or Onyx or other frameworks, and we have importers which convert from these frameworks into MATLAB. So you've designed your network. Now you've got a trained network. The next important step before you go to deployment is actually application design. And this involves writing your application logic, say in a MATLAB script, where you have your application interacting with this inference engine or your deep learning networks. So there's more than just inference here. There is some custom logic surrounding your inference. And finally, once you've got your application ready, you want to deploy it. And this is where we have a couple of code generation products. GPU Coder is a new product we released, which allows you to target these applications to different hardware platforms, including GPUs, Intel CPUs, as well as ARM CPUs. All right. So what are coders? So coders are a set of products that MATLAB provides, which convert MATLAB and Simulink to either C, HDL, CUDA, and whatnot. So we've had the code generation tools that generate C for a very long time, for 20 years or more. And all these coder products are built using our compiler technology that is built in-house at MathWorks. We released HDL Coder about 10 years back, 12 years now. And most of these coders have focused primarily on the controls and signal processing domain. With the emergence of machine learning and deep learning as a major domain, we worked on GPU Coder, which was released last year to generate CUDA code from MATLAB. This is specifically looking at accelerating deep learning applications. So what is GPU Coder? In one slide, it basically converts MATLAB to CUDA code. And you get your CUDA code, you can look at it, you can study it. If you understand CUDA, you can actually understand what it's doing. And it's meant to accelerate any application which exhibits parallelism. And this typically tends to be in image processing, computer vision, signal processing domains. So I'm going to quickly talk a little bit about how these code generation tools work. And then I'm going to show a little demo of how we put this together. Finally, Avi is going to come up and talk about a real application, LiDAR semantic segmentation. So you've heard of semantic segmentation for images. But if you think about LiDAR, this is a pretty hard problem. So we bring all our technology together and show you an end-to-end workflow from training all the way to deployment for solving LiDAR semantic segmentation. So let's start with code generation. So if you want to parallelize your application, you need to extract parallelism. And where is the parallelism in MATLAB? Well, of course, it starts with loops, parallel for loops. That's where a lot of the parallelism is. And then there is vectorized MATLAB. So MATLAB makes it easy for you to express vector math, matrix math, and there could be a lot of parallelism there. And of course, finally, higher order functions like FFTs and BLAS functions and deep learning inference functions, convolutions, and whatnot. So when our code generation tools work, we actually extract custom kernels out of the first two categories, your scalerized MATLAB and vectorized MATLAB. So we can create customized fused kernels. And for the final category, we lean quite heavily on vendor libraries. So for GPUs, we use cuBLAS, cuFFT, cuDNN, quite heavily. Similarly, for ARM, the respective libraries from ARM. And in addition, many of the toolbox functions that are available with MATLAB, for example, in image processing, computer vision, or neural network toolbox, there's a whole array of different functions which enable you to write your application code. And these are highly optimized when you generate code for them. And they're highly optimized for the platform of your choice. So to put it together, our code generation tools are essentially parallelizing compilers. And it involves a whole stack of compiler transformations, including the traditional ones, but specifically transformations which work on loops, allow you to fuse loops, which means fuse kernels together, and generate highly optimized parallel code. So once you get your code, what do you do next, right? So with our workflow, we have different ways of packaging the code. So you get your code. You can run it as something called MEX. MEX is MATLAB executable. And the idea is that if you have C code, you can wrap it in a MEX wrapper and call it directly from MATLAB. Or you can just generate a DLL or a shared library and call it from your C++ code. So how does this all come together? Well, let's say you developed your algorithm in MATLAB. You have a functional reference. You test it out in MATLAB on your host desktop. Ultimately, let's say you want to go to an embedded GPU, right? You want to run it real time. So the process typically involves, well, first, you want to do a deployment test. You want to run it on a GPU, but still stay on your host, and maybe still in MATLAB, so you can actually do the testing in MATLAB. Next, you can move out of MATLAB, but maybe still stay on your host. Use your C++ integration code to test the kernel code that you've written. And then finally, when you're happy with that, you move to a real-time environment. So with code generation, we allow you to do that first by using a build type, the MEX build type, which allows you to run your code in MATLAB, but run the generated code. Or you generate a shared library and integrate it with your handwritten code. Or we can also introduce cross-compiling tool chains to target embedded hardware. So let's take a look at this application's traffic sign detection. So like I said, there are 2 deep learning networks here, and we want to identify traffic signs and label them. So let's look at how this looks, right? So the first step is network design. So MATLAB makes it very easy to build your networks. So there is a lot of affordance to manage your data. So there's something called image data store, which allows you to abstract where your data is sitting. Is it on the cloud? Is it on a different database or on your local machine? And then there's a simple APIs available to build your network structure, what layers you want in your network. And there are options to simply train your network. And that's what it takes to build to train a network like this. So now we have 2 networks, a recognition network and a detection network. So now we want to build our application. So this is the second step. And you can see the first thing we do with the application design is first we run the detection network to find the bounding boxes of the traffic sign. After that, there's actually a whole bunch of code which involves doing NMS, finding the strongest bounding box, doing some resizing before you can call into that recognition network. It's still about 100 lines of code, but you need to write that in order to build this application. And then you can test it in MATLAB very easily. Here, I'm bringing in a video file, taking a frame at a time, and calling my algorithm with 1 frame at a time to see what the prediction is. And I'm timing it to see what the frame rate's like. So this is just running in MATLAB, and MATLAB runs it on the GPU on your host. And pretty good performance is working quite well. So now we'll move on to deployment. So we're going to generate code from this algorithm. So we bring up GPU Coder. And similarly, you can do this for C code as well. And you first start with the function for which you want to generate code for. So once you choose that, the next step is to define its input types. Now, because MATLAB is untyped, but C and C++ are strongly typed, it's good to provide the inputs, the types and dimensions of your input so we can optimize the code. And you can do this by providing a test script which gives us a feeling for what the input sizes will look like. And that's basically it. Oh, we are doing some deep learning, so there's a pop-up which says, what kind of deep learning library do you want to use? So here we have support for GPUs for cuDNN and TensorRT. Similarly, we have support for different ARM and Intel libraries as well. So we choose that, and now we generate code. And the generated when you generate code, you now make a choice as to what is your build type. So here we're going to choose mex so that we can just test it directly on our host machine. So generate code. So this actually generates C++ CUDA code, which you can actually take and use as you wish. You can see there's a mex file generated there. And finally, now we can call that mex function directly from MATLAB by simply calling that mex function from our test script. So now when we run this, we are running the generated code from MATLAB directly. You can still see the traffic signs look good, but the performance is a lot faster. And this is what we get with high-performance deployment. Now, if you want to go to an embedded board, you can choose a static library, and we have integrated support for embedded boards like NVIDIA Jetson TX2 or the Drive PX2 platform. So with that, that shows you the whole workflow from algorithm design to embedded boards. Now, we have support for a whole variety of different library targets, different hardware targets, using cuDNN, TensorRT, ARM Compute Library, Intel MKLDNN library. And this list is going to keep expanding as we move forward, so you can integrate any library into the MATLAB flow. Quick word on the benchmarking. How fast is this? So we have support for all your regular popular networks, but we compared our performance with GPU Coder with TensorFlow first on GPU. So it's a Titan XP. We are benchmarking ResNet 50. And you can see that compared to TensorFlow, we're about 2.5x faster with GPU Coder. Now, TensorFlow also has support for TensorRT, and we also have support for TensorRT. But still, the GPU Coder supported TensorRT is always faster than TensorFlow. On Intel CPU, this is an Intel Xeon CPU. We compared against Intel-optimized TensorFlow. And our generated code is way faster than that. It's about 3.5x faster than TensorFlow. And finally, on embedded benchmarks, this is a Jetson embedded GPU. Once again, we compared with Caffe here. Our generated code is faster. And if you use TensorRT, it uses up more memory. But if you choose cuDNN, we actually optimize for memory as well. So you get low memory footprint. That's what we see also on an ARM. This is on a Raspberry Pi platform. Again, very good performance and low memory footprint. All right, I'm going to switch now to Avi, who's going to talk more about LiDAR semantic segmentation.
All right, thanks, Girish. All right, so through this event, as Girish said, we've talked about kind of taking these standard networks and deploying them on hardware, right? But most of our customers and you application developers don't have standard networks, right? So what I'm going to show you is actually taking a different kind of images, LiDAR. So these are just 3D points, right? X, Y, Z, the distance to the sensor. And if you take a look at what does LiDAR look like, you'll see the video, and then you'll see the LiDAR on the side. Just give you a sense of what it is. It's a very sparse set of 3D points, right? Very different from your standard images. So if you think about it, the ResNets and the AlexNet don't just apply there, right? You have some application-specific things that you need to do. And that's what I'm going to cover here, which is how do you build that LiDAR processing application with deep learning and then get that really high-performance embedded deployment. Right? So now there's a whole workflow to this, right? From accessing the data to finally getting your trained deep neural network. Right? So if you start with accessing and visualizing the data, in MATLAB, you have access to many of these different sensors, including LiDAR sensors. There are customized players and visualizers that you can actually visualize the streaming data. Now, this, again, is true being in the embedded vision. It's true for cameras and for the vision applications as well. But that brings us to pre-processing. Now, application developers don't just take images and put it in a DNN. There's a pre-processing step. So in this case, we take the LiDAR data. We remove the ground plane, just because that adds unnecessary noise. So you see the circles where the LiDAR bounces off the ground. We remove that, right? And then we cluster them. We actually segment each of the objects into individual clusters. But after that comes the challenging, the time-consuming part, and that is labeling the data. If you need to recognize what these objects are, you need to tell the network what it is. Now, in this case, we have the capability to label the data in 3D, and just snapping the bounding boxes onto these 3D clusters actually requires some math and some domain-specific knowledge, and all of that is implemented in MATLAB. Right? But the real kind of magic of using MATLAB is automation. Right? So in this case, just using a tracking algorithm, you can label one frame, and then you can automate it, and it goes in and automatically labels the rest of the frames. And again, this is supported for LiDAR, but we have out-of-the-box tools that do this for vision applications as well, and that is for detection, semantic segmentation applications. Right? And then you have to take your data and you organize it for training. So when the LiDAR data comes in, it looks like that. It's just a set of raw numbers. Right? What we do is we project it to 2D, so it looks kind of like this mask here. And then when you take the labels and overlay it, you get what looks like a semantic segmentation mask. Right? And then as Girish showed, there's a very easy MATLAB API to take to create the network structure. In fact, if you're using a standard structure like a segnet, it's just a single line of MATLAB code to create a segnet architecture. Right? And now that you've taken the data, you've pre-processed it, you've labeled it, you can actually create a LiDAR semantic segmentation algorithm. But this is where the power of MATLAB comes in. We were able to do all of the pre-processing. We were able to do all of the labeling. And then using the code generation tools that Girish talked about, we can take this application and we can put it on an embedded GPU with TensorRT. We can put it in a data center with Intel MKLDNN, and we can also put it on a low-powered part with ARM Compute Library. So MATLAB not only supports the entire application end-to-end, but it really gives you the freedom to choose any of these different platforms. Right? So we're coming up to the end. So just to summarize, so with MATLAB, you get extremely high-performance deep learning inference, and that's what a lot of what Girish showed you. We have a full workflow from prototyping, from getting your data, visualizing it, right up to production. And for the algorithm developers coming up with these techniques, we can automate ground truth labeling. We have lots of domain-specific pre-processing with our image processing and computer vision tools. And like Girish showed with the bounding boxes and non-maximal suppression, when you're building an application, very often you need these post-processing and data analysis tools built in, and MATLAB supports that. So thank you for your time. I think we have a couple minutes for questions.
Thanks very much, Avi and Girish, for an excellent presentation that finished on time. Just want to point out the microphone in the middle of the room for any comments or questions that anybody has. Anyone? I've got one to start it out. So tell me about your implementation platform choices. How do you decide as a company which platforms you're going to support, and what guidance do you give to your customers as to which one might be appropriate for their needs?
So we usually try to stay pretty platform agnostic, but how we decide how we support is just purely based on customer demand.
Okay.
So things like we started by supporting GPUs. Customers asked us to support Intel and ARM, so in the next release we came up with Intel and ARM. So we're listening to the market, and depending on what our customers are asking us to support, we're investing in those areas.
Okay. And then once you support a certain CPU architecture, ARM or x86 or something like that, again, support for new variants of the architecture, new generations of the architecture, that's again driven by customer demand, or do you do in some cases, proactive support on your own based on what you assume will be demand?
It depends also on how closely mapped they are to the previous generation. So if the library directly supports them, it's easy to just uptake on the vendor library support.
Got it. Okay. Any comments or questions from the audience? Here we go.
Okay. So the question is that do you have like a deep learning toolkit which contains examples of end-to-end that you just showed in terms of when you get the kit from MATLAB, it has pre-built examples of doing different applications?
Yeah, so we have a lot of examples. If you look at those links there, there's a free on-ramp tutorial which actually walks you through a lot of that. And the landing page actually has a whole suite of different networks and models that you can start playing with.
Okay, thank you.
Anything else? Going once, going twice. Okay, it's break time. Thanks very much, guys.
Thank you.